Okay, right now you can see an H-bridge. H-bridge is just, okay, sorry. I'm providing back context. Right now we have a lab view not going yet. This is an H-bridge. So what the premise, okay, let me give you some background. What I'm primarily doing with this whole thing, with the whole charger itself, it's supposed to be an electric power system for a Cub-Satellite. You might ask, why are you doing this small scale, whatever? It's to give hindsight and also background information, also reference of data, like here, the switching, of what is going on. What is our safety features? How can someone learn this, and how can someone reference this? Because primarily, I'm not going to be working on this the whole time. I would like to, but in essence, I have classes, I have this and that, I have job, stuff. So, providing a background information, I have a solar panel. Celsius. I have a solar panel here. Solar panel provides 12 volts and 20 watts. P equals V times I, like my last video. Power equals, or the power, which is 20 watts, the voltage is power of 20 watts, equals 12 volts times current. 20 divided by 12, you do the math in your head, it's about 1 something amp, or close to 2 amps. Full. And this is nominal, typically. Right here is the BQ charger. I was originally going to use test points with the ESP32 LabVIEW. That was just too much. What I am going to do to savor this and split it, because I understand I can plug so much into LabVIEW, my USB-Cs. I made an individual LabVIEW. You might say, you just said LabVIEW. It's separate. It doesn't directly connect to my computer as much as certain. It connects to a different port in a specific address. What I mean is I connect it to a Keysight oscilloscope. I identify the IP address. I use Visa serial, then wrote individual commands individually towards it. Pull the data, read it, plot it, log it. Read it, plot it, log it. I'm going to start saying that now. And I just use the 2 points, measure the ground, measure. And on the oscilloscope, it'll show it and also log the data all the way to LabVIEW in an Excel, which then live. So, boom, logging data. Start the data log, stop it. There you go. We don't need the ESP32, we need all that breadboard. No, we don't. Now we connect the output of the battery to the battery 3BMS with the 3 series. There's 3 LiPo batteries in series. Lithium ion batteries are going to be in series. 3.7 volts nominally, which when I measured was not 3.7, it was 3.53. And 3.5458. And the total voltage that I measured was 10.58. The current is going to be the same because they're in series. Within that, we know that we expect a nominal voltage about, because when you ship a battery, when someone ships a battery, it's not fully charged. It's typically because there's legal bounds, there's regulations and stuff for that. We get 10.58, but in reality we can do 12 volts. The BMS, the purpose of the BMS, the battery management system, is where it restricts overvoltage, overcurrent, undervoltage, undercurrent. Internally it's pre-programmed and it does it adjust based on the resistor. So it finds the input voltage and then adjusts accordingly based on what is nominally on a reference of 12 volts. What I mean reference is it compares the 12 by the resistor, it takes a constant value and then compares it and then stops and cuts it off. Only enables when it is getting a voltage above the current battery voltage, and so current, and then cuts off if it is under, whatever. If it's under, it cuts off to 0, it does not release. I connect a buck converter, which is an LM2576 3.3. I have specific parts for it. I just need to wait for the LM2576 and the inductor for it. Inductor is 150 microhenry, rated for 2.7 to 3 amps. It's accommodated, it has the specific DCR for it, the internal resistance and current rating, particularly for this model, within recommendation TI. There's no point in making your own buck converter when this already solves your problem. This is a little motor driver. It's a motor driver. It's efficient, it's used, it's a regulator, it's good. You just need to get the diode, the flyback diode, the Zener diode, the capacitors for filters, and the inductor. That's it. You do the math and TI provides the equations for you. I do have a separate, which is in that. This will be powering the ESP32 or STM32, whatever they're using. Over here, I have which this 2 amp fuse, I haven't decided yet. Most likely I'll keep the 2 amp fuse just in case, and then I'll have a 2N222 BJT transistor for a safety current shutoff. And I'll state that within the document saying, this cuts off at this level, based on this reference, based on this, and based on these tests. All this, within that, this has a safety factor, double safety factor for the H bridge, because everything can go to shit. This can shut off and whatever. Which the load right now is going to be the magnet torquers. You might say, what are magnet torquers? Within a Cub-Satellite, you don't want to use ion propulsion. There's no necessary need. It's going to be a low Earth orbit. It's going to be in a perfect spot with the Earth's magnetic field. You would use an X, Y, and Z axis. These are coils. You would induce a certain current, which that load, there's going to be 3 separate H bridges. This individual circuit is not fully bound. There's going to be switches here, and then transit resistor. That's oscilloscope. DMM, the digital multimeter. This specific accommodation for it and this goes forever. There are individual ICs that already condense this into a little thing that solve this issue. This solves the big because this can be very big scale. I'll show you in a second. It solves it, but this proves the circuit that I just built right now, what I built last night, proves the concept in practice. This specific IC. This is I'll talk about it later. But these I'll have each individual for a magnet torquer, X, Y, and Z. The X-axis will be specific current. Within that, we'll do. Okay, there it goes off. Let me turn the power source off because ESP32 is probably going to switch and all that crazy. X, Y, and Z, you induce a specific current. You have a magnometer and you have an IMU. The magnometer senses the Earth's current. I would have that, of course, away from the magnet torquers. The magnometer measures the Earth's magnetic field, which is 26 microteslas or in the 20s microteslas. Within that, converts in towards the IMU into a control dynamics aspect. You use Euler, whatever, that's the control dynamics team to do that. My job is to make sure everything works in a power and also sensing general aspect. The IMU, the magnometer, the IMU, math, then it gives us say-so whether to push current in towards the specific magnet torquers, which then after doing the calculations, you would adjust accordingly based on do this one time, then do this, that to orientate the satellite based on the Earth's magnetic field. It's done complexly. This is where kind of, not rocket science, this is where advanced electrical engineering kind of comes in. Well, I wouldn't say that, but okay. It does that and adjusts accordingly. That's it. Buck will be powering the individual controller that controls these. And all it is just a matter of switching the pinning. You would have background information. This is for embedded systems people too. The background information for people, for whatever STM32. Right now we're going to have 3 H bridges for 3 magnet torquers. We are going to have an magnometer and IMU. That is so easy to do. We just bag them back. That I'm going to do that last. Magnometer. Once I build the perf boards, which are perf boards of the specific magnometer for each magnometer, which I need to buy more. I need to buy more these NMOS and PMOS and NMOS power transistors to build more of them, and then accommodate ESP32 over 1 and STM32. Within that, you can buy the magnometer IMU. That's what I have so far. Everything tested perfectly, and I will show data. I'm not show publicly, whatever, but I'm going to show data to the electrical lead at the end. When we do a further test, or I'll show you all. I mean, it's not a big deal. When we do individual tests, which I'm going to do a basic rundown test, when I get everything done. Because this tested perfectly, this tested perfectly, this tested perfectly into measuring 10.58. I need to get this finalized with some parts, the motor driver. This is already done. With that, next video, we'll be talking about the exact simulation of the transistor. Or the H bridge, sorry.